All right, welcome back to the deep dive. Today we're gonna be tackling something pretty cool, blind face restoration.
Ooh,
Yeah, so this is basically, you've got an image, and it could be really bad quality.
okay.
It could be low resolution, could be blurry. It could have, all sorts of things wrong with it. Compression artifacts. Maybe it's an old JPEG,
Right.
but we wanna get back a nice clear image of the face. And we don't know how the image was degraded in the first place.
Yeah, that's blind. That's where the blind comes in?
That's where the blind comes in.
Yeah.
So you can think about like old photographs that you might have,
Mm-hmm.
or maybe you're working with some security footage, right?
Yeah.
And it's really grainy. You're trying to make out who it is in the video.
Definitely so many real world applications.
Absolutely,
Mhm.
it's really hard in the real world because
Right.
it's not just um, it's not just a simple blur that we're trying to deal with.
No, no, I mean you have so many different factors that go into the degradation. Like you said, motion blur, noise, all these compression artifacts from, saving it as a JPEG too many times. And then on top of that, you have to take into consideration, the diversity of human faces, the different poses, expressions, lighting.
All this stuff.
So,
That's
yeah,
it's a lot.
it's a really challenging task.
So how do we even begin to tackle this?
Right.
And today we're going to be talking about something called the generative facial prior, or GFP.
P.
So this isn't like it's not a real physical thing,
Right.
but it's the knowledge that has been learned by a generative adversarial network, or GAN,
Right.
specifically a face GAN. So like StyleGAN.
Yeah,
This thing's been trained on tons and tons and tons of faces.
exactly.
And so it's really good at knowing what a face should look like.
And all the features that a realistic human face would have.
Exactly.
All the variations of that. Yeah.
So how do we I guess before we kind of jump into how we use that,
Yeah.
what were some older methods, before we kind of had this ability?
So previous methods would often rely on what's called a geometric prior.
Okay.
So trying to find specific facial landmarks, where are the eyes, where's the nose, where's the mouth?
Oh.
Or they would try to use a reference prior. So they'd look for, maybe a high quality image of a similar face and kind of use that as a guide to restore the degraded image.
So almost like a nearest neighbor type of thing.
Kind of, yeah, exactly. But
Really?
you can imagine, especially with really, really low quality inputs, that those methods would struggle.
Yeah, like if you can't even make out where the eyes are in the first place,
Exactly.
it's gonna be hard to find those features or landmarks.
Yeah, it's really hard to estimate that geometric structure when your image quality is so low. And then, when it comes to the reference priors, even if you can find a high quality image, getting a good match that really captures the individual and, has the same pose and expression
Yeah.
can be really tricky, especially if your library of reference images just isn't that diverse.
Right.
So you can see how these methods kind of fall short, especially when the degradation is really severe.
Yeah, it's like, if you're trying to, if you lose a puzzle piece, you can kind of maybe guess what's supposed to go there.
Yeah,
But if half the puzzle's gone, like you're really lost.
you're gonna have a hard time.
Yeah, exactly.
Yeah,
So that brings us to GFP GAN, right?
right.
Which is what we're gonna spend this whole deep dive talking about.
Exactly.
And this is a method that uses that generative facial prior that we talked about, to basically do a better job at blind face restoration.
Yeah, right.
So let's kind of jump into this and see how this actually works.
Okay.
Okay.
So the GFP-GAN framework has a few different modules that all kind of work together.
Okay.
So the first one is called the degradation removal module.
Degradation removal module.
Oh, and this uses a UNet architecture.
Okay.
Have you heard of UNet before?
I have, yeah. I
Hmm.
think it's been on some previous episodes.
Yeah.
I can't remember the details though.
Yeah, so it's a really common architecture in image processing, especially when you're trying to do things like segmentation or restoration.
Okay.
And it has this encoder-decoder structure with these things called skip connections.
Okay.
So the encoder basically takes your image and kind of compresses it down,
Okay.
extracts the important features, and then the decoder takes those features and tries to reconstruct the image.
Okay.
And the skip connections help to preserve some of those, low-level details.
Right.
Which is really important for, making sure that the restored image looks realistic and doesn't have any weird artifacts.
Mm-hmm.
Then you have the pre-trained face chain, which is the heart of this, GFP.
Okay.
So in this case, they used StyloGene too.
Salesian too.
And these two modules, the UNet and the StyleGen2, they communicate with each other through something called latent code mapping.
Latent code mapping.
And then the final piece of the puzzle is these channel split spatial feature transform layers, or CSSFT.
CSFT, yeah.
Which is a mouthful, but we'll get into that.
Yeah.
So basically, the idea is the UNet takes that degraded image, tries to clean it up a little bit.
Okay.
And then the latent code mapping takes those features from the UNet and finds a corresponding code in StyloGen2's latent space.
Okay.
And then those CSSFT layers, they kind of blend the features from the UNet with the generative power of the Jan.
Okay.
And you get your final restored face.
Okay, so it's like the UNet's trying to like clean up the mess.
Yeah.
And then the StyleGen's kind of like, well, I know what a face should look like, so let me just fill in the blanks here.
Yeah, exactly. It's providing that prior knowledge.
Exactly.
Yeah.
Okay.
So let's break down each of those components a little bit more.
Okay.
So that degradation removal module, the UNet, that's doing some really important work.
Yeah.
Because like we said, these real world degraded images, they're really messy.
Yeah.
You have blur, you have noise, you have these JPEG artifacts. Maybe the resolution is super low.
Right.
So the UNet's job is to kind of mitigate all those problems.
Okay.
Try to reduce the blur, suppress the noise, get rid of the JPEG artifacts, even try to recover some of that lost resolution.
Okay.
So it's doing a lot of heavy lifting right at the beginning.
Yeah, it's kind of doing the dirty work.
Exactly.
Okay. And I remember you mentioned that the UNet architecture itself is really well suited for this.
Yeah.
So why is that?
So the UNet is really good at this because of those contracting and expanding paths that I mentioned.
Okay.
So those paths give the UNet a large receptive field, which basically means it can see a wider area of the image.
Okay.
And that's really important for dealing with these, spatially extended degradations like blur.
Okay.
Because, blur affects a large area of the image, so you need to be able to see a lot of the image to correct it properly.
And just like one pixel that's wrong.
Exactly.
It's like a whole region, right?
Yeah.
Okay.
And then those skip connections that I mentioned, those are really important because they allow the UNet to preserve those fine-grained details.
Okay.
The little things that make the image look realistic.
Right.
And that's important across all those different resolution levels. So,
Right.
You might have a low resolution image and then the UNet is trying to upscale it.
Okay.
And those skip connections help to make sure that you don't lose those details as you're upscaling.
Okay, so it's kind of like it's got like a magnifying glass on the finer details.
Exactly. Yeah, it's trying to make sure that those details are still there even when you zoom in.
Right. Okay. And then so during training, how do we encourage this UNet to actually do what we want it to do?
So during training, they use this thing called L1 restoration loss.
L1 restoration loss, okay.
And they apply that at each of those resolution scales within the UNet.
Okay.
So basically, the L1 loss is just measuring the difference between the output of the UNet and the ground truth image.
Okay.
And they're doing that at each of those different scales. So it's kind of like intermediate supervision.
Okay.
It's telling the UNet, okay, you're doing a good job here, but you need to do a little bit better at this resolution level.
So it's kind of like it's getting feedback at each step of the way.
Exactly. Yeah, it's getting feedback and it's learning to progressively refine those features and produce a cleaner representation at each stage.
Gotcha. Okay. So we've kind of got this UNet now that's giving us a cleaner version of the image.
Yeah.
But we still need to tap into that StyleGen too,
Yeah.
right? That pre-trained face Jan.
Right.
So how do we actually do that?
Right. So this is where that generative facial prior comes in.
Okay.
And like we said, the pre-trained Jan, StyleGen2 in this case, that's what embodies that GFP.
No.
It's all that knowledge of facial structure and appearance that it's learned.
Right.
So traditionally, if you wanted to use that prior knowledge, you would do something called Jan inversion.
Jan inversion.
And basically what you would do is you would try to find a latent code in the Jan's latent space.
Okay.
That when you feed it back into the generator, it would produce an image that looked like your degraded input.
Okay.
But the problem with those inversion methods is they often require a lot of computation. You have to do this iterative optimization, which can be really expensive.
Right.
And then on top of that, the latent code that you get might not actually capture all the nuances of the original face.
Okay.
You might lose some of the finer details in the reconstruction.
So it's kind of like a lossy process.
Yeah, it can be, yeah.
Okay.
So GF Bishan takes a different approach.
Okay.
So instead of trying to directly invert that degraded image into the GAN's latent space, they use those latent features that were extracted by the UNet.
Okay.
And they map those to the GAN's intermediate latent space, which is often called W.
Okay.
And they do that using these things called multi-layer perceptrons, or MLPs.
MLPs. Okay.
Yeah.
So it's kind of like a translation layer.
Yeah, exactly. It's translating from the UNet's feature space to the GAN's latent space.
Gotcha. Okay.
Yeah.
And so the idea here is to kind of find a code that's already, representing a plausible face that's related to the input.
Yeah, you're basically finding a good starting point in that latent space.
Right.
Instead of trying to force the degraded image to fit perfectly.
Right.
So you're avoiding that computationally expensive inversion process.
Right.
And you're also, trying to preserve more of those finer details.
Right, because you're starting with something that already kind of knows what a face is supposed to look like.
Exactly. Yeah.
Okay, that makes sense.
Yeah.
And then I remember earlier you mentioned that this approach can also help with color enhancement.
Yes.
Especially for old photographs.
Yes. So what's really interesting is that these generative models, they don't just learn about shape and texture. They also learn about the distribution of colors in faces.
Okay.
So because StyleGen 2 was trained on this huge data set of color images, its latent space has all this information about, realistic skin tones, eye colors,
okay,
all that stuff.
So we can kind of tap into that as well.
Exactly, yeah.
Okay.
So by mapping the UNet's features to that latent space, you have the potential to not only restore the structural details of the face,
right,
but also add realistic color back into an image that might be black and white or faded.
That's pretty cool.
Yeah, and it can all happen in one step.
Okay.
You don't have to do this separate colorization process.
Right. Okay, that makes sense. So we've got the UNet kind of cleaning things up.
Yeah.
We've got the latent code mapping kind of putting us in the right spot in StyleGen 2's latent space.
Right.
But how do we make sure that we're actually reconstructing this specific person's face?
Right.
Right. It's not just like a random face that just happens to be, realistic looking.
Yeah, we want to make sure we're preserving the identity of the person in the original image.
Exactly.
And that's where those CSSFT layers come in.
CSSFT.
I remember those.
I do.
Yeah, so basically we need a way to take those specific details from the input image
Okay.
and inject them back into the GAN's generated features.
Okay.
So that the restored face actually looks like the original person.
Gotcha.
And there's this technique called spatial feature transform, or SFT.
SFT. Okay.
That provides a way to do this.
Okay.
So what SFT does is it uses spatial features from one source,
Wow.
in this case the UNet,
Okay.
to modulate the features of another source, in this case the GEN.
Okay.
And this modulation is spatially aware.
Spatially aware.
Yeah. So it's basically saying, okay, the GEN knows what an eye looks like in general.
Okay.
But the UNet has given us some specific information about the shape and position of this person's eye.
Okay.
So let's use that information to fine-tune the GEN's output.
Gotcha. Okay. And how does it actually do that?
So the SFT layer basically learns to generate these things called affine transformation parameters.
Affine transformation parameters.
So these are basically just scaling and shifting values.
Okay.
And it learns those parameters based on the spatial features from the UNet.
Okay.
And then it uses those parameters to modify the GAN's features. So it's like saying, okay, we need to make this eye a little bit wider.
Okay.
Or we need to move it a little bit to the left.
Yeah. Okay.
Based on what the UNet is telling us.
Gotcha. So it's like it's taking those spatial features from the UNet, and it's kind of like a blueprint.
Yeah, exactly.
To tell the GAN how to kind of warp and shift and move things around.
Yeah, exactly. It's like a guide.
Okay, that makes sense. But then if we're just using those features from the UNet,
yeah,
what's to stop us from kind of like overfitting to the bad parts of the image, right?
That's a good point.
If the UNet hasn't quite gotten everything perfect, like how do we make sure we're not like adding those imperfections back into the final image.
Right. So the researchers behind GFP-Jan, they realized that that was a potential problem.
Okay.
If you just use a standard SFT, you might end up relying too much on those, potentially still degraded spatial features from the UNet. And you might lose some of that, really high quality realism that the Jan can provide.
Right. So it's kind of like a double-edged sword.
Exactly, yeah.
Okay.
So to address that, they came up with this channel split SFT.
Channel split SFT. Okay.
So instead of applying that SFT to all of the Jan's feature channels, they split them into two groups.
Okay.
One group gets modulated by the UNet features,
Okay.
and the other group just gets passed through directly.
Okay.
So the group that gets modulated, that's the one that's responsible for preserving those specific details.
Okay.
Making sure that the restored face looks like the original person.
Right. So that's like the identity part.
Exactly.
Yeah. Okay.
And then the group that gets passed through directly, that's the one that's responsible for the realism.
Okay.
Making sure that the face looks like a real face.
Gotcha. So it's like we're taking the best of both worlds.
Exactly. Yeah, you're combining the strengths of the UNet and the Jan.
Okay, so it's kind of like I don't know, it's like you're making a cake and you've got,
Sure.
got your batter and you've got your frosting.
Yeah.
And you want the batter to be, moist and delicious, but you want the frosting to look really pretty.
Exactly.
And so you're kind of keeping them separate, but you're combining them in the end to get the best of both.
Yeah, that's a good analogy.
Okay, that makes sense. So we've got this architecture now.
Right.
Right? We've got the UNet, we've got the latent code mapping, we've got the channel split SFT.
Mm-hmm.
But how do we train this thing?
Right.
Like what are the like the rewards and the penalties that we give it during the training process to encourage it to actually do what we want it to do?
Right. So that's where the loss functions come in.
Loss functions. Okay.
Yeah. So the loss functions are basically just mathematical functions that tell the network how well it's doing. And you need a good set of loss functions to train a network like this because it's doing a really complex task.
Right.
So the first loss function is the reconstruction loss.
Reconstruction loss. Okay.
And this is just trying to make sure that the output image looks like the ground truth image.
Okay.
The high quality image that we're trying to get back to.
Right.
And they actually use a combination of two different losses here.
Okay.
They use L1 loss, which is just measuring the pixel-wise differences between the two images.
Okay.
And then they also use perceptual loss.
Okay, perceptual loss. Okay.
Which uses features from a pre-trained VGG19 network.
VGG19. Okay.
To compare the two images.
Okay.
And the reason they use perceptual loss is because it's more sensitive to things that humans would notice.
Okay.
So it's not just looking at the pixels.
Right.
It's also looking at the higher level features of the image.
Gotcha. Okay, so it's kind of like if you're looking at two pictures of a cat.
Yeah.
Right. Like they might have slightly different pixel values.
Right.
But to a human, they both look like a cat.
Exactly. Yeah.
And so the perceptual loss is kind of trying to capture that human perception.
Yeah, exactly. It's trying to make sure that the restored image not only matches the original image at a pixel level, but also that it looks like a real face to a human observer.
Right. Okay, that makes sense. So what other loss functions are we using?
So the next one is the adversarial loss.
Adversarial loss.
And this is a pretty standard loss function when you're training Jans.
Okay.
And basically you have this discriminator network.
Discriminator network.
That's trying to tell the difference between real faces and faces that were generated by the generator.
Okay.
And then the generator is trying to fool the discriminator.
Okay.
It's trying to generate images that look so real that the discriminator can't tell the difference.
Gotcha. So it's like this little game that they're playing.
Yeah, exactly. It's like a cat and mouse game.
Okay.
Mm-hmm.
And so why are we doing that? What's the point of having this adversarial loss?
So the adversarial loss is really important because it encourages the generator to produce realistic textures and fine details.
Okay.
It's trying to make the generated images look as statistically similar to real faces as possible.
Gotcha. Okay. And then you mentioned earlier that there was a facial component loss.
Right.
So what's that all about?
So The facial component loss is basically just focusing on specific parts of the face,
Okay.
like the eyes and the mouth.
Okay.
And they do that because those are the areas that people tend to focus on when they're looking at a face.
Right.
So you want to make sure that those areas are really high quality.
Right, right, right.
And so they use these local discriminator networks
Rule discriminator networks.
that are just looking at those specific regions.
Okay.
And they're trying to tell the difference between, a real eye and a fake eye.
Okay.
Or a real mouth and a fake mouth.
Okay, okay.
And then they also use this thing called a feature style loss,
Feature style loss.
which is based on Gram matrices.
Gram matrices.
And I won't get into the details of Gram matrices.
Okay.
But basically, it's a way of measuring the statistical relationships between different features in an image.
Okay.
And so by using this feature style loss, they're encouraging the generator to produce more realistic textures in those key facial regions.
Gotcha. So it's like if you're looking at a painting, you might not be able to tell the difference between a real painting and a fake painting just by looking at the brush strokes.
Right.
But if you look at the overall style of the painting,
Uh-huh.
the way the colors are blended, the way the light is used, you can start to see those differences.
Yeah, exactly. And that's what the feature style loss is trying to capture.
Okay. Okay, that makes sense. And then finally, we need to make sure that the face that we're restoring actually belongs to the same person.
Right.
Right. We don't want to just generate a random face that just happens to look realistic.
Right. We want to preserve the identity.
We want to preserve the identity. So how do we do that?
So for that, they use the identity preserving loss.
Identity preserving loss.
And this uses a pre-trained face recognition model called ArcFace,
ArcFace, okay.
which is really good at extracting those unique features that identify a person.
Okay.
And so the identity preserving loss is basically just measuring the distance between the ArcFace features of the restored image and the ground truth image.
Okay.
And by minimizing that distance, they're encouraging the generator to keep the same identity,
Okay.
even after all this restoration.
So it's like we're telling the model, like, hey, you can do all this fancy stuff. You can clean up the image, you can add details, you can make it look realistic. But at the end of the day, it still needs to be the same person.
Exactly.
Okay.
Yeah.
Okay, that makes sense. So we've got all these different loss functions. We've got the reconstruction loss, the adversarial loss, the facial component loss, the identity preserving loss.
Right.
They're all kind of working together.
They're all working in concert.
to train this GFP-Jan.
Exactly.
So how did it actually do?
Right.
Like, did it actually work?
So they did a bunch of experiments.
Okay.
They trained GFP-Jan on this huge data set called FFHQ,
FFHQ, okay.
which is a data set of high-quality facial images.
Okay.
And then they tested it on a bunch of different benchmark data sets.
Okay.
Some of them were synthetic data sets where they basically took these pristine images and they artificially degraded them. And then they also tested it on some real-world data sets that had inherently low-quality images.
Okay.
Like images that were scraped from the internet.
Right, right.
And so on those synthetic data sets, they found that GFP-Jan outperformed a lot of the other